Hi, I'm Gary Millette, and this is ELE-180, Instrumentation and Measurement. This is the spring of 2023. This is topic number 4, Quantities and Units of Fundamental Concepts. So let's get started. So there is what we call the International System of Units, and they should be familiar units to most people. This chart that I've got here shows the basic units of certainly time, length, and mass, which are second, meter, and kilogram, and it shows the symbol there for each one of those. They're the fundamental units of physics. Then we have electric current, which is the ampere, thermodynamic temperature, which is basically in degrees Kelvin, although we're more familiar with Celsius and Fahrenheit. Amount of a substance, unless you took chemistry, this may not be familiar to you. It's called a mole, and we'll have some examples. And then luminous intensity is the candela, or CD is its symbol. So let's take a look at length for a second in terms of the laser world. Well, in the laser world, we have wavelengths of nanometers. The top one of these diagrams here shows the short to long wavelengths, and it turns out there's a blow up or an inset, if you will, of the visible. And way over on the top left, we have 10 to the minus 12th, well, which looks like it's not right, meters, but maybe that is correct. Cosmic rays, very short wavelengths. Then there's gamma rays. X-rays are 1 nanometer. So yeah, I guess it's right. And of course, X-rays we know are dangerous to us, as well as gamma and cosmic rays. Ultraviolet is close to the visible light. On the other side of the visible light is the infrared. And we're talking 1,000 nanometers there. Then microwaves, we have microwave ovens, then radar, 1 millimeter wavelengths, then radio waves, 1 meter, and then down below kilometer wavelengths to the broadcast band, which we consider long wavelengths. So the insert or inset is the visible light, and you can see purple down to red there. Red is closest to infrared, purple is up by the ultraviolet. And notice you see 400 nanometers to 700 nanometers. So those values should be familiar to you in your study of lasers and light. The standard unit of mass is the kilogram, and it's equivalent to about 2.2 pounds. Of course, the unit for time is a second, and we're all familiar with clocks. There's an old analog clock here. So let's just talk a little bit about time with lasers, and I've got this graphic which comes from IPG, and it turns out on the left-hand side we'd see nanosecond lasers, large heat-affected zone type of machining. You see the long pulse laser beam. What happens, you have ejected material, you have a melt zone, you have micro cracking of the material. There's heat transfer to surrounding materials, damaged surface, a recast layer, the stuff that comes out that's molten and cools down, surface debris. It's not a very clean or nice way of machining. If we use ultra short pulse lasers, we have a smaller heat affected zone. We don't see any micro cracking, no shock waves. What happens is no debris, no recast layer, and what happens is we tend to have a very nice well-drilled hole there with a no melt zone, a hot dense plasma down the bottom of it, no micro cracking, again as I mentioned before. So who makes picosecond and femtosecond pulses for lasers? Well, people like IPG do. Here's some of their devices for ultra-fast pulse lasers. And picoseconds would be 10 to the minus 12. Femtoseconds, 10 to the minus 15th. Now, changing gears a little bit, here's a wire. We define current as a flow of charge. 1 ampere is 1 coulomb per second. And if we want to talk about heat, here we have a infrared camera that shows us the heat emanating from this particular resonance in the background there. And on the right-hand side, you can actually see a smartphone with an infrared camera. So they're about $200 to $300 for the adapter to make your smartphone into an infrared camera. One that should be of particular interest to us would be the luminous intensity or candela. And here this diagram shows a light source. We have a light receiving surface at a distance d. We have 1 square meter. We have a solid angle A. And it turns out the unit for luminous intensity is the candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of a certain frequency, 540 times 10 to the 12th hertz, and that has a radiant intensity of that in that direction of 1/683rd, yes, watts per, I think, can't see it behind my head here, steradian, I think. And that 1/686 watts, I think, is what the intensity of a candle is. So I mentioned before, if you had taken chemistry, you might have heard of a mole. And notice this says chemist's definition of a mole. So 6.022 times 10 to the 23rd particles. They could be atoms, molecules, ions, formula units of a substance. And again, the mole was used by chemists to come up with some of our things like amperes and coulombs and things of that nature. So here's some examples of a mole of substance, and you see, mercury in a flask up there, H2O next to it, mercury in a beaker, H2O in a flask, sulfur, various other types of chemicals, copper, lead, and so forth. All those things are supposedly in 1 mole of those substances. Now we have derived units of angular measurement, and one of those for angle, we have the radians, and the solid angle is a steradian. Radians are used when doing calculations involving sine waves, and steradians are typically used when doing calculations involving antenna patterns and laser beam intensity. So here's a radian. A radian is something like 53.7 degrees. Here's a steradian, and what happens, we get an area on the surface of r squared at a distance of r from the center. So what about units of energy? Well, the standard units of energy are the joule, and it turns out the joule is defined as 1 kilogram per meter squared per second squared, where we use a Newton per meter. Newton is the unit of force. So mass times velocity squared, and so on and so forth. Power is energy per time. 1 watt is 1 joule per second. And those are not easy to remember, those guys. So turns out there's a lot of electrical quantities, symbols, and derived SI units. There are many units for electrical quantities, and since lasers are electronic devices, you should be aware of these various units which describe or characterize electronic components or parameters. So in this chart you see capacitance with a symbol C, unit of farads with a symbol F. Charge has a symbol of Q. Unit is coulomb and symbol C. Conductance is G, Siemens, or symbol S. Energy is symbol W. Unit is joules, symbols J. Frequency is F, and notice it's lowercase f. And the units are hertz, which are capital H, lowercase z. Impedance is Z, ohms, and omega. Inductance is L, henries, or H. Power is P. Unit is a watt, or symbol W. Reactance is X for the SI symbol, or rather SI unit. Reactance is ohms, and again the symbol is omega. Resistance is R. SI unit is also ohms. Symbol is also omega. And voltage V, SI unit volts, and symbol V. So again, you're going to come in contact with these things all the time. So here's some example of components. I show all kinds of different types of resistors here. Carbon and metal film on the left. Thick film, thin film resistors on the left also. Wire wound special purpose resistors in the middle. Adjustable resistors on the far right. Again, a lot of components you might come in contact with. Capacitors are shown here, and again, there's a wide range of how we make them and so forth, what they look like. The big tubes are electrolytic capacitors. On the top right and kind of the right, you have variable inductors. Those are air variable inductors because we have plates that turn into or mesh with other plates, but there's air between the plates. And then we have all kinds of other types of capacitors down below in the bottom across that picture. How about inductors? Inductors are basically coils of wire, and here shows all kinds of possible inductor configurations. I've added on the right, you might notice that the top picture in the top right has a wire, but the wire is coated with copper, and then I have toroid inductors below that, right above my headshot. How about magnetic quantities, symbols, and derived SI units? These things you don't come in contact with as much. Magnetic field intensity, magnetic flux density, magnetomotive force, permeability, mu, reluctance as a script R. So these symbols are not as commonly recognized as the electrical ones, but nevertheless they are what we use today. Now that kind of finishes off that little part of this presentation. Let's talk about scientific notation now. It turns out that we like to use powers of 10. It's a form of shorthand for us when we talk about electrical quantities and so forth, because it turns out there's such a wide variation in the values we come up with for things like farads and ohms and so forth. So this chart shows you 10 to the 6th is 1 million, 10 to the 5th is 100,000, 10 to the 4th is 10,000, 10 to the 3rd is 1,000, 10 to the 2 is 100, 10 to the 1 is 10, and 10 to the 0 is 1. Anything to the 0 power is 1. That makes the mathematics complete. On the right hand side we have 10 to the minus 6, which is a millionth. 10 to the minus 5th is 100,000. 10 to the minus 4th is 1/10,000. 10 to the minus 3 is 1,000. 10 to the minus 2 is 100th. And 10 to the minus 1 is 1/10. So we like to use powers of 10 as a shorthand notation for those numbers. So engineering notation and metric prefixes, well, that's limited to powers of 10 that are multiples of 3. And here's some examples. For instance, 82,000 is expressed as 82 times 10 to the 3rd. 243,000 expressed as 243 times 10 to the 3rd. And 1,956,000 expressed as 1.956 times 10 to the 6th. And what are these metric prefixes? Well, I'm not going to go over them all here, but you're probably familiar, most people probably familiar with, if we go on the top there, centimeters, millimeters, micrometers, nanometers, picometers, and femtometers. I mentioned that earlier about the femtosecond and picosecond lasers, laser pulses. But there's also atta, zepto, and yocto, it looks like, which is 10 to the minus 24. On the large size, we have hecto, kilo, mega, giga, tera, peta, exa, and then zeta and yotta. Maybe influenced by Star Wars. And again, certainly influenced by computers. We talk about the amount of data we transmit. So interesting enough, as soon as you get to mega, everything's a capital. You notice when you go below 1, or in decimals, they're all lowercase. But deca and hecto and kilo are also lowercase. Kind of interesting. Now, that says, the date on this says 2023. As of 2023, we've come up with some new prefixes. We've had to invent some new ones. There's ronto, which is 10 to the minus 27th power. There's quito, if I pronounce it correctly, 10 to the minus 30th. On the other side of that, there's rana, 10 to the plus 27th, and kuka, 10 to the plus 30th. And again, I probably murdered those, but again, you probably haven't heard of these, and you probably haven't heard of a lot of the ones on the prior slide, but what happens is they, I'm sure, as time goes on, and our measurement techniques get better and better, we'll probably introduce those. So you see that we go from plus 10 to the plus 30th to 10 to the minus 30th. That's 60 powers of 10. So as a review here, we've talked about electric and magnetic quantities, symbols, and units. We've taken a look at shorthand notation, scientific notation, putting things in powers of 10, engineering notation, and then metric prefixes, which allow us the engineering notation. And new ones become common terms as technology marches on. So let's review again Ohm's law. Here we show excuse me, a power supply with a voltmeter across it. And we have an amp meter which is measuring the current in a load R. So we have two of these setups, and on the left hand side you see a certain voltage. It looks like there's about 6 of those red lines, and it looks like there's about 3 of the red lines for the current meter. On the right hand side, notice the voltage has gone up. There's more red bars, and what's happened to the current? It's gone up. So basically this shows us Ohm experimentally determined that doubling the voltage applied to a load would double the current in the circuit. This is known as what we call a linear relationship. So Ohm's law provides the relationship between current, voltage, and resistance. Here now we have a battery with a certain resistor, a 10 ohm resistor, and on the right hand side we've got a battery, the same battery, with a 20 ohm resistor. And if you take a look at the red bars, the voltages are the same for both of those circuits, but on the left hand side we have a lot of current, and the right hand side we have half the current. So Ohm also discovered the following: if the resistance in a circuit is doubled, the current is halved, which is an inverse relationship. So here are Ohm's law equations. I equals V over R, V equals IR, R equals V divided by I. So if the voltage V and resistance R are known, then one may calculate the current I. If the current I and the resistance R are known, one may calculate the voltage V. If the voltage V and the current I are known, then one may calculate the resistance R. All these three equations are tools that may be used to solve for circuit values. Now, Ohm did this, and we should, take notice of it, that if we do an experiment where we have a variable voltage source and we have a constant load resistance, we can measure the current, and if we plot that result, we will get a straight line. So that graph depicts a linear relationship. Ohm's law is a linear relationship. I've added another curve here. Today we like to plot the IV curves of components. This is called characterization. So what's this graphic for you laser people? It turns out shows the IV curves of different color LEDs. Note the different turn-on voltages. So the first one you see is IR for infrared. On the far right you see UV for ultraviolet. Those are again out of the visible range. Then we have red, orange, green, yellow, blue, and white LEDs. And again, they all have a different turn-on voltage. That is the voltage you have to apply before they start emitting. And notice that once they start emitting, the curves somewhat are linear, but they're not quite exactly linear. And they're certainly nonlinear as they turn on. So here's Ohm. I won't belabor this. Energy and power definitions. What about this? Energy is the ability to do work. Power is the rate at which power is the rate at which energy is used. So power is energy divided by time. Power equals watts per second. So I have more units here. Energy is measured in joules. We said that before. Time is measured in seconds. Power is measured in watts. By definition, 1 watt is the amount of power when 1 joule of energy is used in 1 second. So an equation for this: energy equals power times time, or W equals P times T. What about the kilowatt hour? Well, when the electric utility company charges you for your electricity usage, it's on the basis of the amount of energy that you have used, not the power. Hence your bill for kilowatt hours. What about power in an electric circuit? Well, I show a bunch of equations here. These equations are similar to Ohm's law. There are 3 forms of the power equation. One should use the equation appropriate to the situation. So we have power equals V times I in the top left. Power equals I squared R, the top right. And we manipulate things there, and we'll get power is equal to V squared over R in the bottom of the slide. So where does the power go? Well, here's a circuit shown in figure 4.1. And basically I've got a battery and a resistor. Well, what happens is the current goes through the resistor and heats it up. So for these academic examples, the power supplied by the battery just becomes wasted heat. In some cases, this is a technique used to heat a residence. We call it baseboard electric heat or space heaters. So what about energy conversion and voltage drop in resistance? So in this circuit, we see the voltage source, the battery on the left-hand side, and load on the right-hand side. And we know the electrons move, so we show the electron flow here. As the electrons flow through the resistor, there's an energy drop going from bottom to top. The electrons have higher energy or negative on the negative side of the circuit. Electrons have lower energy on the positive side of the circuit. So the electrons in this diagram lose energy as they pass through the resistor. Hence there's a voltage drop across the resistor, and you want to note the polarity of the voltage across the resistor is the same as the polarity of the battery. What about DC power supplies? Here's a power supply connected to a DC load. It turns out the output goes to the input, and the minus output goes to the minus input of the electronic load. And by the way, everything needs power for any electronics. So efficiency of electronic power supplies is given by this equation. Efficiency is power out over power in to the power supply. So power out is equal to power in minus a power loss. So what form does power loss take? Again, wasted heat energy. And here's joule, and here's watt. And that's it, I think, for this presentation.